This lecture series summarizes the book Back to Reality, a revision of the scientific worldview. Its main message is how to make sense of reality, to explain the unity of nature that displays itself in data of various kinds. That is, skewed distributions, sigmoidal curves, power laws are found everywhere. It's only the names that we have given to things that are different. For example, the shape of a mollusk spiral shell is akin to that of a spiral galaxy. Various distributions also look alike. For example, microbes are much more abundant than big animals, and likewise local stores vastly outnumber shopping malls. Growth curves are also similar. For instance, both biota and business grow along S-shaped curves. Also, flows of air, avalanches in semiconductors, and stock trading exhibit chaos resembling our chaotic brain activity. Since the boundless similarity, coined as the grand regularity, ranges from atoms to galaxies and from retail to world trade, could it be that everything in the universe is fundamentally composed of one and the same substance, and hence everything is alike? Indeed, thought Parmenides, the ancient philosopher envisioned that both matter and space are made of the same eternal elements, which he called atomos, meaning non-divisible. While the atom of the 19th century was found to be divisible into elementary particles and the particles further transformable into nuclear reactions in the vacuum and vice versa, exchange of any kind entails that everything is in a sense the same substance. Although the ancient idea of a fundamental element may seem vague, it is in fact a strict axiom. It's either true or false. There are no parameters to be adjusted or added. When everything is composed of the indivisible and permanent elements, nothing can emerge from nothingness and nothing can vanish into nothingness. But everything depends on everything else. Despite its consistency, the old unified understanding might seem not to be of much help to us. Because in those days, not even the four fundamental forces of nature were known. Even so, Parmenides' thesis implies that gravity, electromagnetism, and the weak and the strong nuclear force too are made of the fundamental elements. Maybe this is exactly the insight that we need now. We know that the photons mediate electromagnetism. We should therefore ask whether this holds true for the other three forces as well. These thoughts should not be held as an exaltation of the foregone philosophers, but rather as an invitation to consider what we might learn from their admirably sound reasoning. The early thinkers aimed to uncover general principles that set everyday experience into logical order. Now we seek to discover a universal law that sets both scientific experiments and everyday experiences into a consistent form. Like Parmenides, Newton queried in his book of optics, "Are not cross bodies and light convertible into one another?" Today, it is posited that the plethora of particles and their interactions are all manifestations of quantum fields. Even so, shouldn't we strive to visualize these fields to see what determines the particle properties and what mediates gravity, if anything?
What is light?
The ancient atomistic idea was put into practice in the early 1800s when John Dalton grasped that chemical substances are compounds. Then the enormous multitude of molecules could be organized in terms of a relatively few atoms. However, 100 years later, when Hans Geiger and Ernst Marsden, led by Ernst Rutherford, showed that the atom itself consists of a nucleus and electrons, the classic question arose again. What is the indivisible elemental entity? Is there one? In the mid-1920s, the American chemist and physicist Gilbert Newton Lewis, who coined the word photon, put forth anew Newton's inkling that particles of light could be the fundamental element. Even before Lewis' proposal of the light quantum as the basic element, the German-born mathematician Emmy Noether had written her famous theorem about quanta. It relates a system's energy and time to its amount of quantum. And since the universe is a system, we can calculate from its total energy and age that it contains on the order of 10 to the power 120 quanta. This number, with its 120 zeros, is unimaginably huge, yet finite. In this way, that is to say, in theory, it was understood that the photon is the fundamental element of everything. But in practice, the thesis was not seen as convincing. The total number of photons did not seem to be constant. Specifically, an atom may go from an excited state down to the ground state, either directly emitting only one photon or via intermediate states emitting one photon at each stage. Since the number of detected photons depends on the route taken, it looked as if the photon appeared out of nothing and disappeared into nothingness. So it became a truth of physics that the photon could not be the indissoluble element. Despite all its theoretical sophistication, physics is an empirical science. If a hypothesis goes against observations, it must be rejected. Of course, the thesis should and eventually will be re-evaluated if it turns out that something has gone unnoticed. Then again, the theory itself predisposes how we comprehend the phenomena. Comprehension in turn determines our understanding of what needs to be measured. The Hungarian-born philosopher Imre Lakatos even contended that no observation would suffice to prove a theory wrong. Although a theory may appear in conflict with the data, we cannot conclude what causes the disparity without some theorizing.
What is the vacuum?
If we were only to mince matter into smaller and smaller bits, wouldn't we eventually come across the indivisible basic building block? Well, let's see how that goes. Compounds divide into atoms. Each atom, in turn, breaks into nucleus and electrons, and the nucleus split into protons and neutrons. Each of them consists of three entities. They're called quarks. Oddly, the quarks cannot be detached from each other. Instead of the quarks breaking apart, more anti-quark and quark pairs will materialize the harder the particles are smashed into each other. Where do these matter-antimatter particles in pairs come from? It looks as if they pop out of nothing. In that case, the bookkeeping of substance would be like a worst-class fraud. In truth, the particles do not come from mere nothingness, but from vacuum. While there is no matter in the void, it isn't just empty space either. A cubic meter of vacuum consists of the energy of about 1/1000th of a joule. This amount of energy is equivalent to that of a few hydrogen atoms. But in the void, there is no matter at all. So what is the vacuum? This is the big question of physics. Our ignorance is immense because the void is all pervasive. But we do have a clue. In all of space, free of matter, there is as much energy as there is energy in all of matter. The galaxies are scattered so far apart from one another that the energy bound in matter in the whole vast universe is on average just 1/1000th of a joule per cubic meter. Is this correspondence just a coincidence? Hardly. How could such a mutual energetic balance between the void and matter have come about and lasted over the evolution of the universe unless matter and vacuum are able to transform from one another? In some circumstances, they must comprise the same essence, the quanta. It isn't a coincidence either that Earth's gravity is in balance with its mass, but an equivalence stated by the law of gravity. Likewise, the void must be a gravitational field of all matter. The gravity of the entire universe is not a distant backdrop, but a real hindrance we sense every day. When you step on the gas pedal, you feel that you're being pushed to the back of the car seat. Conversely, you will continue in motion in the event of a sudden stop, unless the seatbelt restrains you. Isn't it amazing that the whole universe reacts against you when you make a change? The visionary physicists Ernst Mach and Dennis Sciama thought, as Newton did, that the distant stars are what causes inertia. Their conclusion is easy to absorb. Gravity decreases inversely with the distance, and the number of galaxies increases with the distance squared. So, the overall effect grows with distance. Due to the numerous far-flung galaxies, universal gravity is very, very stable. How can the distant universe resist the change in motion instantaneously here on Earth? This bothered Newton a lot. Feynman was already wondering about the same thing as a kid. He had noticed that when he tugged a wagon, a ball on it rolled and banged on the tailgate. And when he halted the cart, the ball bumped against the front edge. So the young maverick asked his dad why this happened. And the dad said, "Well, nobody knows," declared Elder Feynman. "The general principle is that the things which are moving tend to keep on moving, and the things which are standing still tend to stand still unless you push them hard. This tendency is called inertia, but nobody knows why it is true." The cause of inertia has remained unknown until the realization that all-embracing void space is the gravitational field of the universe. It's all around us, and that's why it affects us in real time. This is nevertheless not enough for an explanation of inertia. We must also know what the vacuum is. We have to understand how the fundamental elements make it up, just as Parmenides argued, and we still need to comprehend how the vacuum couples to the matter. Only then we will genuinely know what inertia is. A good swing ride gives you a gut feeling for gravity and inertia that is more memorable than anything you can get from a lecture or textbook. Isn't it amazing that all riders, even the empty seats suspended from a carousel, align in the same angle? It's because both gravity and centrifugal force, due to the inertia, are proportional to the mass. Einstein understood that this equivalence is no coincidence, as the gravity of the whole universe is the source of inertial effects. General relativity was devised to incorporate this idea, but in fact failed to do so. Einstein himself emphasized this failure, as the British cosmologist Schema pointed out in his iconic paper on the origin of inertia in 1953. Even though Einstein's model of the vacuum gives the right numbers, curved space-time without any substance is a strange idea. After all, the vacuum embodies energy and has electromagnetic properties. How could there be content and properties unless there is some substance? The conventional interpretation of Michelson and Morley's experiment refutes the light-mediating ether hypothesis. It does not, however, exclude the possibility that the vacuum itself is light. This idea seems strange at first sight because the void is dark and transparent. How could the void be quanta of light and yet invisible? Photographers and bird watchers know the answer by experience. When coated with a thin film, the lens of a camera or telescope reflects remarkably little light. Actually, the light waves are reflected from both the lens and a coating film, with the photons from the two surfaces combining so that the crest of one then fills precisely the trough of another. And hey presto, we see no light as the waves of the opposite faces nullify each other. However, the photons themselves have not disappeared but make up the pair that moves on. The out-of-phase pair is not detectable by the eye or camera because the two photons cancelling each other's electromagnetic forces do not displace electric charges. But the photons themselves have not vanished from existence. They're still moving at the speed of light. As such, could it be then that these pairs are whistling all over the universe and thereby embodying the vacuum? The idea is surprisingly simple. So, has it not been proposed before? Well, in a way it has. Faraday thought that the lines of force are themselves substance, and hence he saw no need for a separate substratum through which transmit actions. Maxwell advanced this idea by mathematizing the electromagnetic field as a strange state of the void. He pictured light as undulations of ether, so the ether is, in his view, light. At the end of the 20th century, the British physicists John Poynting and Oliver Heaviside concluded from Maxwell's equations that the energy of the ether propagates at the speed of light. However, they did not have the concept of light quantum to account for the sense of the void. Planck's great discovery was still a decade off, and Lewis' interpretation of the photon as the primary constituent even further away in the future. Before those revelations, the experiments by Michaels and Morley was interpreted as if the void was nothing. As special relativity agreed with the observations, Einstein went on to formulate general relativity. Curved space-time is ether without substance. This mathematical model of gravitation works all right, but still fails to explain why bodies move toward each other. Also, the mathematical model of electromagnetism works well, but does not explain why charges move relative to one another. Explanations need substance. According to modern physics, the quanta of light are created out of the vacuum, but now we understand they are, in fact, being singled out from the vacuum's paired quanta. Likewise, the modern tenet contends that the photons vanish into nothingness. Now we understand that they in reality match pairwise to merge into the transparent vacuum. Feynman graded the double-slit experiment as the only phenomenon whose examination calls for quantum mechanics. Yet now that we know the substance of the vacuum, we can comprehend the experiment with common sense. As a particle moves, it perturbates the void as a ship makes waves in water. When the particles pass through one of the slits, the void waves that it has generated also pass simultaneously through the other slit. These waves then deflect the particle before it hits the detector. In other words, the particle experiences the vacuum wave to which its own motion gave rise, and hence interference pattern forms. There is no reason to believe that the particle miraculously goes through the two slits at the same time. The obtained understanding of the vacuum as the paired photon substance does not per se call into question quantum mechanics, as we can frame the wave function as a mathematical image of the wavy void around the particle rather than the particle itself. For example, the photon produces vacuum waves of its own kind. The electron generates waves that are typical of the electron. Likewise, the waves of a boat are typical of a boat, and the waves of a ship are characteristic of a ship. It is thus our concepts that are revised, not so much of our calculations. Quantum mechanics models an interference pattern that results from numerous events. Its weakness is that it does not describe any one of those events. Based on the Copenhagen interpretation, the passage of particles through the slits is arbitrary. It's an excellent model of the vacuum quanta that are moving in all directions at the speed of light. While convenient in computation, however, randomness is devoid of physical meaning. How could there be any effect without some cause? To hold quantum mechanics as the truth rather than as a mathematical model, one has to imagine that nature is random. Then one would have to be believing in miracles. It's worth emphasizing that the physical nature of the vacuum does not imply determinism, as Einstein and David Bohm are thought to have assumed. The future is not predetermined, but neither is random. The vacuum affects the electron, and the electron affects the vacuum. Likewise, our environment acts on us, and we act on it. When everything depends on everything else, the equation for the flows of quanta can be formulated, but it cannot be solved.
Where do the photons come from?
A few years ago, researchers at Chalmers University of Technology managed to shake visible photons 2 by 2 at a time out of the vacuum. Faraday had already speculated that light could be produced by shaking the lines of force. By all appearances, the wavelets of light, both as single and paired, embody the vacuum. Our experience tells us that there are bodies enveloped in fields, say the Earth in its gravitational field. Because a particle is also a body, there is a field around it. In contrast to this lucid logic, the standard doctrine claims that the particle itself is an excited state of the quantum field. Say, electron is an excitation of the electron field. But what do these words mean? We cannot relate the idiosyncratic concept of modern physics to our experience of reality. That has led us to a hornet's nest of problems. Isn't it the vacuum around the particle, rather than the particle itself, that is the excited state that the standard theory talks about? We need to find out what the particles look like. Logically, they must consist of quanta, as the vacuum does. How else, if not by exchange, could there be a local and universal energetic balance between the void and matter? Particles emerge from the vacuum and submerge into it, as has been vindicated on many occasions.
What is matter?
Newton's vision of light and matter as the same substance suggests that particles are quanta of light. Faraday concluded similarly that everything, both matter and the void, must be one and the same substance. After all, the lines of electromagnetic and gravitational force in space emerge from matter and end in matter, as well as curving and whirling around the matter. Let us therefore ask how photons could make up elementary particles. The light quantum is like a small string. It stretches, shrinks, and twists, but no force can cut it into pieces. When we consider how bits of string, that is, the quanta of light, could make an elementary particles, the facts already available in the standard model leave little room for the imagination, but still plenty for another viewpoint. Is there a particle comprising only one photon? What is the simplest shape you could loop from an elementary piece of wire? The neutrino is the tiniest particle we know. Its angular momentum equals Planck constant per orbital period, just as a photon's momentum equals Planck constant per wavelength. In other words, a neutrino spins about itself. Is the neutrino a circling quantum? We can test the idea that the neutrino is a loop quantum. The loop is a mirror image of itself, just as a wave is a mirror image of itself. This strikes a chord. Neutrino is thought to be its own antiparticle, just as the photon is known to be its own antiparticle. As the photon winds into a circle, the wavelets, electromagnetic crest and throw cancel each other out. This makes sense, because the neutrino does not evince electromagnetic properties. A loop curves differently than a wavelet. The difference in curvature shows itself as the mass of the neutrino, for mass means curvature. By contrast, the photon is massless because its curvature is identical to that of the paired photons that make the void. That's why the whole space weighs nothing, even though it holds as much energy as all the matter in the universe. The neutrino is completely planar, but a cosmos, although immensely large, is not absolutely flat. The universe is slightly curved because it contains matter, albeit on average very little. When passing by the completely planar neutrino, the photons of the vacuum slightly straighten their trajectories, which manifests itself as the neutrino's mass. Therefore, the neutrino does not move entirely free, namely precisely at the speed of light in the vacuum.
What does the electron look like?
Let us suppose that also the electron is made up of photons. What could it look like? Where does the electron get those properties that the photon lacks? These are electric charge, magnetic moment, and mass. In 1823, André-Marie Ampère suggested that the electron is a serpentine-like circular coil, for he knew by experience that electric charge relates to the number of windings of a copper wire. He also knew that the magnetic moment was proportional to the coil's cross-sectional area. You can easily make a wireframe model of Ampere's electron. Just strip off a helical spring of the back of a notepad or take a slinky and bend it into a full circle. When the ends meet, the coil makes a seamless toroidal ring. But how many loops are there in the electron torus? Ampere did not know that. Only half a century after his death, the natural constant, known as the fine structure constant, that reveals the electron structure was measured. The value of 1 over fine structure constant is 137 plus. It denotes the ratio of the total length of the torus to the length of a single quantum, the neutrino loop. The constant hints at how many loops there are in the overall helical coil that rises like a corkscrew. Due to the rise of the thread, known as the pitch, one quantum trails the other in a slightly retarded position along the helix. Throughout the 137 loops, the lag amounts precisely 1 quantum, so that the electron torus has exactly 138 quanta. The quanta circulate in the compact torus. This internal motion, so to say trembling, is a standing wave, as Schrödinger concluded from the Dirac equation in 1930. More recently, David Hestenes has expressed the solution of the Dirac equation as a closed helical path of photons. The pitch of the torus forces apart the surrounding paired photons of the vacuum, manifesting as the electron's electric field. Likewise, the curl of the torus causes vorticity around the surrounding photons, manifesting as the electron's magnetic field. The torus also explains the mass of the electron. Since the loops of the opposite side of the torus curve almost opposite directions, the photons of the vacuum, when inbound, bend in one direction, and when outbound, bend in the opposite direction. So the net effect of curvature is small, and hence the electron's mass is small. The electron torus complies with the standard model, as its corkscrew geometry matches the symmetry group of the electroweak force known as SU2. This chiral symmetry means that the electron and its mirror image, the positron, are different particles, in the same way as the left hand differs from the right. The Chinese-American physicists Chung-Dao Li and Cheng-Ning Yang anticipated this, and Chien-Shiung Wu proved it in 1956. The result was sensation. Wolfgang Pauli jested, "I can't believe God is a weak left-hander." The torus also makes sense of the decay of the electron to the W- boson. In that process, the loss of one quantum, a neutrino loop, introduces a narrow gap in the torus. The electron is indeed divisible into its elements. The textbook claims that the electron is a point-like particle, but how could a dimensionless pinprick possibly have properties such as magnetic moment? In contrast to this contrived idea, the quantized torus is consistent with data, as researchers concluded from their measurements. Quote, "If the electron is a composite particle, its constituents are strongly bound, giving the electron the observed point-like quality at experimentally accessible energies. So these constituents, the quanta in their tight coil, are strongly bound to one another like the strongly bound quarks." If we did not know the structures of both vacuum and the particle, but only the corresponding equations, we would be bewildered, as are most physicists today, about the fact that it takes 2 revolutions for an electron to return to its initial state. Undoubtedly, one spin would bring the electron to its initial position in the emptiness, but not in the vacuum. The second round unwinds the twist of the vacuum quanta that the first one introduced to the electron-coupled field. You can demonstrate the unwinding of a winding by holding a book on your palm and swinging your arm once below and then once again above your shoulder, as Alexander Unziker, a clear-thinking German physicist, shows in his video Quaternions and Fundamental Physics in 2020. The electron torus leads us to the structures of other elementary particles. The positron is an antimatter particle, the mirror image of the electron. When a particle meets an antiparticle, they annihilate each other. However, not to vanish into nothing, that is, at nihil, but rather their quanta escape into the vacuum. The structures of the electron and the positron suggest that the tori open and unwind so that the quanta discharge pairwise into the void. We do not see these photon pairs devoid of electromagnetic force but we do witness the two out-of-phase photons emerging from annihilation in opposite directions. The two stems from the unwinding of the opposite electric charges.
What do the proton and neutron look like?
In 1964, the physicist Murray Gell-Mann at Stanford and Georg Zweig at CERN realized that the proton and neutron are composed of three elementary particles, which became known as quarks. The proton consists of two up quarks and one down quark. The neutron consists of two down quarks and one up quark. But what are the quarks made of? Because the charge of the up quark is 2/3 of a positron charge, could it be an arc of the 2/3 of an arc of the positively charged torus? Because the charge of the down quark is 1/3 of the electron charge, could it be an arc of 1/3 of the negatively charged torus? This straightforward inference of the quark structures agrees with observations. When a proton and an electron transform into a neutron, the charges cancel out. The idea that the quarks are fractional structures of the electron and positron is not exactly new. In 1974, Howard Geiger and Sheldon Glashow reasoned that the proton ought to break into positron and the pion. The pion, also known as the pi meson, is a particle that comprises a quark and antiquark. While there has not been any sign of a spontaneous proton decay to this day, their fundamental idea of unity is worth recalling. They say, all elementary particles, strong, weak, and electromagnetic forces are different manifestations of the same fundamental interaction involving a single coupling strength, the fine structure constant. Geiger and Glashow wrote, continuing, our hypothesis may be wrong and our speculations idle, but the uniqueness and simplicity of our scheme are reasons enough to be taken seriously. As a torus comprises 138 quanta, the down quark is made of 1/3 of them, that is 46 quanta, and the up quark composing 2/3 of them, that is 92 quanta. The toroidal helix winds along the arc so that the short wavelength photon, known as the gluon, connects one quark to the next at an angle of 60 degrees. Thus, in a particle composed of three quarks, such as a proton or a neutron, the three quarks cannot but reside on the faces of an equilateral pyramid. This tetrahedral symmetry is consistent with the rule found by Gell-Mann and Zweig, known as the strong interaction gauge group SU3. The proposed proton and neutron structures, while surprisingly simple, explain the properties of the particles. The total number of windings gives rise to the electric charge. In proton, the two up quarks contain positive windings and the one down quark negative windings, totaling the charge of +1. The neutron is neutral because there are as many as right-handed as left-handed threads. The magnetic moments of the closed quantized curves can be calculated in the same way as the moment of the closed current loop. The proton moment is much larger than the neutron moment because the quantized curve of the proton encloses a much larger area than that of the neutron. The results agree with measurements. The proton and neutron are much heavier than the electron. The vacuum couples with the proton and neutron much more strongly because the arcs of quarks are imperfect without the opposite curvature, unlike the full torus. The masses calculated from the wireframe models comply with the measurements. Moreover, we see from the wireframe models that the quarks cannot pivot about the gluons rather freely, but they cannot be pulled apart. For the gluon, as the short wavelength photon, is uncuttable. In this way, we understand the property what is known as the asymptotic freedom. At times, I have stood at my front door, trying out keys to find the right one. Eventually, I gathered that it helps to turn the middle key of my three keys upside down, whereby I can also distinguish between the two right side keys. Of course, the keys can also be labeled with different colors, for the label does not change the key itself. In neutron, as in the three keys on a chain, there is one down quark before the up quark and another one after the up quark. However, in quantum chromodynamics, a type of a quantum field theory, the locus of one quark relative to the other is not recognized, as the particle structures are not known, and hence the quarks are stamped with a label known as the color charge. In reality, the quark does not carry a color charge, as this would imply symmetry breaking, of which there is no sign. Let us face it, the standard model is imperfect. It has features that exist only in the imagination.
What happens in a nuclear reaction?
Now that we know the structures of the reactants, we can grasp a nuclear reaction. Consider an electron next to a proton. Its store is opening up by losing one of its neutrino loops along an antineutrino. When the electron opens up, it becomes a W- boson, a highly reactive particle that annihilates with the adjacent up quark in the proton so that the quanta uncoil pairwise into the vacuum. The up quark discharges completely and the gluon leaves it behind, latches onto the ends of the remaining arc of the W- boson, which then, accepting the backlot of the lost neutrino, becomes a new structure known as the neutron. 200 years ago, chemistry was an abstract, non-figurative subject like elementary particle physics today. Then Dalton realized that compounds react in integer ratios because they are composed of atoms. Now you realize that the elementary particles react in integer ratios because they consist of quanta. About 100 years ago, scientists worked out how atoms bond together. Now similar possibilities are had with particles. We can construct models of elementary particles from models of quarks and even predict exotic particles. Quanta move from one particle to another in nuclear reactions in the same way as atoms move from one compound to another in chemical reactions. Moreover, in cyclic reactions, particles convert from one form to another over and over again in the same way as metabolites circulate in organisms and nutrient cycles in ecosystems. Such circulations are also manifestations of the grand regularity.
What is the Higgs boson?
The Higgs boson, the glorified God particle, decays among other things into 2 electrons and 2 positrons. This tells us that the particle has certain symmetry. An open torus at each face of a tetrahedron explains the particle properties, charge neutrality, mass spin, and its symmetry, as well as Higgs boson being its own antiparticle. The mass of the Higgs boson is enormous, being made up of 2 linked W- and W+, or equivalently 2 Z bosons that mediate weak nuclear force. These particles are massive because the strings of the vacuum quanta couple tightly to the narrow single neutrino white slots of the open torus, similar to the fork gets caught up in strands of spaghetti. The masses of many exotic elementary particles derive from such structural details, which can be seen as imperfections when considering the electron's pure circularity. Against this backdrop of tangible thinking, it's evident that it's the paired photon vacuum rather than the postulated Higgs field that endows the elementary particles with their masses. Physicists wonder why elementary particles can be grouped into 3 families. Each family has the same members. Their characteristics are very alike, only the masses of the second family are higher than those of the first, and those of the third are higher still. The similarity of the particles across the 3 families is akin to the chemically similar elements belonging to the same group in the periodic table. Copper, silver, and gold are very alike but differ by mass. Likewise, electron, muon, and tau particle have the same charge and almost the same magnetic moments, only their masses differ. According to the intuitive logic, the fundamental element, the quantum, should adopt the same geometric shape in each member of a given family. The elementary planar loop of the first family is known as the electron neutrino. We do not know the geometry of the loops of the second and the third family in detail, but we may rely on the ground regularity and envision that the surroundings of increasing energy, the planar neutrino twists around itself like a rubber band twists. Twisted light in itself is a well-known phenomenon. When the neutrino goes through space and matter, its mass varies. This oscillation tells us that the electron neutrino twists in the muon neutrino and further into the tau neutrino to gain a balance with the stuff it goes through. A chemical compound, such as a microcycle, also twists from one conformation to another, depending on conditions. So, a biologist would say that on its way the neutrino adapts to its environment. Well, a physicist could say the same. After all, the photon also adapts to the gravitational field by shifting its period.
Which view on reality is right?
Wolfgang Pauli demanded the verifiability of science with his legendary retort, "It's not even wrong. Unless a theory is clearly stated, it cannot even be critiqued." Abstract thoughts are hard to check against reality, whereas the idea that everything is quanta can't be proven wrong. For one thing, the Tene would trivially turn out to be false if quantum were to split. For another, if energy were found to stay constant in an event. Einstein shunned quantum mechanics. He regarded action at a distance as an impossible fable. How could a measurement of one particle possibly betray the attributes of another in less time than the light takes to cover the distance between them? Instantaneous violates causality. Non-local is non-causal. This odd notion of action at a distance concerns an experiment where two photons are emitted from the same source at the same time in opposite directions. Each of them ends up at its own detector. When the phase of the electromagnetic field of one of the photons is registered, it is immediately known that the phase of the other one is the opposite. That corollary itself is not odd because the radiated photons were mirror images of each other as they departed, so that until and including the event of detection, they cannot be anything else than the opposite by their phases. However, according to quantum mechanics, the photon phase is indeterminate until it's detected. In other words, when the phase of one photon is measured at one detector, only then is the second photon assumed to take the opposite phase at the other detector. This creates the extraordinary impression that the information of the photon phase is transmitted from one detector to the other faster than the photons themselves move. By common sense, understanding of the experiment cannot even be called a challenge. So long as the photons maintain their phases on their way to the detectors, we know at once from the phase of one that the phase of the other must be the opposite. For example, if the phasor of one photon happens to point at 6 o'clock relative to the other detector, we immediately know that the other points in the opposite direction at 12 o'clock. When the experiment is explained in this way, there's nothing spooky about it. We just don't know the photon phase before it's measured. In fact, the photon has a definite phase only relative to the reference phase. That is to say, for example, the detector. If the detector were pivoted upside down, the photon phase would be the opposite. Likewise, a clock dial phase without numbers cannot by itself tell us what time is. From this operationalist perspective, the hands do not indicate any time until compared, for example, to the vertical direction. Quantum mechanics translates this ignorance to absurdity that Einstein memorably dubbed, "Is the moon there if nobody looks?" Well, for sure it is, for vacuum embraces everything, and hence nothing escapes interactions like a detection. Einstein, as most physicists for decades, was confused about action at distance because the photon phases are in fact not detected. Instead, the photons that make to the receiver are counted. Specifically, when the phase of a photon happens to be 45 degrees, the probability of recording the photon on either one of the two channels is proportional to the phase projection, which is a cosine of the angle. That is, a cosine of 45 degrees is about 0.7. Although it's equally likely for either channel to catch the photon, the probability of registering the photon on one or the other is not half but 0.7. Does the probability exceed 1 when both channels register a photon with a probability of 0.7? This concern reminds me of a legendary phrase by a Finnish ski jumper. It is 50-60 how it will go. In the experiment we have the same situation as in real life. Only one of the alternatives will happen. The probability of registering the photon with the 45 phase is 0.7, although the number of captured photons is likely to be almost equal for both channels. In the same way as the photon arrives at the receiver, we can think of going through a doorway. The probability of getting straight through is proportional to the width of the opening in the front of us. When we see the doorway at an angle of 45 degrees, then approximately 70% of the width is visible to us. So, when two doorways on either side of a corner are equally visible, the overall width is 0.7 plus 0.7, which equals 1.4. Even so, we do not go through both openings, but through one or the other. When we face one of the openings straight on, it is visible to us by full width, whereas the second opening is not visible at all. Then the total view is 1 plus 0, which equals 1. The difference between the total views of the two detectors is at largest when the faces of the two receivers are 45 degrees relative to each other, and least when that is 0 when the receiver faces are parallel. If one erroneously expects the photon registration to be independent of the detector view, one sees discrepancy between the expectation and reality. The difference must be explained. The adventurous explanation is that the states of the photons are entangled and leads to the illusion of the spooky action at distance. Even after 100 years, the troublesome interpretation has not faded away. The photons start off and remain in opposite phases. The measurement merely reveals the phase difference between the detectors, known already at the onset. Thus, the entanglement belongs to those of a historical concept of science which were once vehemently defended and verified by experiment, but still came to nothing. Quantum mechanics is a tool. Today, also a taboo. Some scientists trust, even defend, a doctrine they do not comprehend. If we believe that reality is, as it is presented by modern physics, fundamentally incomprehensible, we will be prone to accept other authorized but unwarranted things. Today, quantum mechanics is upheld by referring to Bell's theorem, which says that the quantum mechanics is incompatible with hidden variable theories. Indeed, but that's not even the issue. The action at a distant experiment is only about detecting the photon phase. In a sense, the Michelson-Morley experiment was a conjuring trick. Since the void was not seen as ether, the objectives of physics became defocused. When the theory of relativity inhibited our viewing of the vacuum as a physical substance, instrumentalism took over. We got wave functions, pseudoparticles, and virtual photons, but we did not get explanations. The split view of the void as abstract on the one hand and concrete on the other was echoed in the dialogue between Einstein and the Nobel laureate Dutch physicist Hendrik Lorentz. In 1917, Lorentz reasoned, "It is always risky to close a path of research completely, and perhaps it's good, considering everything together, to grant the ether one more chance. Conceivably, a time will come when speculations over its structure, from which we now abstain, become fruitful and effective." Dirac considered the possibility that the vacuum consists of quanta that propagate at the speed of light. Robert Lawlin, the professor of physics at Stanford University, deems it's regrettable that theoretical physicists are ill-disposed toward ether. Relativity does not itself exclude the existence of such matter, provided that it complies with the symmetry of space-time. In his book, A Different Universe, 2005, Lawlin continues, "About the time relativity was becoming accepted, studies of radioactivity began showing that the empty vacuum of space held spectroscopic structure similar to that of ordinary quantum solids and fluids. Subsequent studies with large particle accelerators have now led us to understand that the space is more like a piece of window glass than ideal Newtonian emptiness. It's filled with stuff that is normally transparent but can be made miscible by hitting it sufficiently hard to knock out a part. The modern concept of the vacuum of space, confirmed every day by experiment, is a relativistic ether. But we do not call it this because it's a taboo. Well, taboo silences, and so we fail to deal with the problem. While many experiments have irrefutably shown that particles materialize from vacuum, others have proven that the ether cannot be a light-transmitting medium either. The dilemma accentuates the discordant character of modern physics. A particle seems too real to be only a transient quantum field on the one hand. The luminous ether, however, seems unrealistic on the other. How could it be superbly mobile, at the same time a stiffer and more elastic substance than steel to transmit light? So those who deny the ether are illogical, while those who hold on to it are irrational. Rather than choosing sides, we should seek a solution to the problem. When quantum mechanics is advocated by arguing that it reproduces data, the whole point is missed. Why are the results correct, even if the ontology is empty? All that ultimately matters is that what can and cannot be explained by the paired photon void. When there are alternative ways of interpretation, Newton advised, the truth is ever to be found in simplicity and not in the multiplicity and confusion of things.